So now in this video we have the 555 timer. This is an NE555. I should have wrote 555 there, but I forgot. I did update that on the diagram before I uploaded it to Patreon. But we're going to replace this mechanical switch with a light dependent resistor. But first let's review what this circuit does. The output is off, it's low. That's the stable state. Monostable is one stable state until we press the switch. Then the output goes high, but then it goes back to low after a time set by the capacitor and resistor there. We have a 1 kilo ohm resistor with a 1000 microfarad capacitor, so we have about 1.1 second that the output goes high before going back to its stable state of low. So the switch, let's measure the voltage going to the trigger pin, and let's zoom in a little bit. We don't need to see the schematic anymore. I went over that in a lot of detail in the last video. I'll try to link that in the description. But we will look at the voltage, making it to the trigger pin, and usually I falsely trigger it right when I connect the meter, but you can see it's 5 volts. That's because we have the pull-up resistor until I press the switch. Then we get 0 volts. And if I hold 0 volts at the trigger pin, then the output will stay high until right when I let go of it, as long as we pass the time of the capacitor. But if we give a shorter than 1.1 second pulse there, going to the negative rail, you can see the output stays high for about 1.1 seconds. And if we hold it, you can see it stays at 0. So we're going to take a light dependent resistor and just put it parallel to the switch to begin with. We're making the exact same connection, so we could still use the switch as we normally would. But now enough light is falling on the photo, the light dependent resistor I mean, so that its resistance is lowered enough that we have dropped to below about 1/3 of the power supply voltage. That's what this is actually looking for, not necessarily 0 volts, but less than about 1/3 of the power supply voltage. And we can look at that right now with the meter there, and you can see 1 volt is less than about the 1.7 volts that 1/3 of 5 volts is. If I put my hand over it, I start shading it, you can see the voltage is going up. That's because we're getting more resistance towards the negative rail. And again, we could keep I can cover this and then still use the switch normally, and because I have enough resistance on the light dependent resistor that it's holding the voltage up, but the switch will bypass that, of course, if we close it. So let's just get rid of it though. And instead of the 10 kilo ohm resistor, I find with the light level I have right now, the 4.7 kilo ohm resistor works better. So that's going to hold up the voltage a little bit better. We will see that when we measure this. But still, the light dependent resistor, if you get enough light on it, it gets down to about 0 volts. So I'm finding somewhere above 1.8 volts is when we have a high signal as far as this integrated circuit is concerned. So I don't have enough light on it. Let's tilt the light dependent resistor a little more towards the light. There you can see we're slightly below. So now we're given a low enough signal to trigger the 555 timer. If I put my hand over it, now the voltage is high enough. So there's a point about 1/3 of the power supply voltage where the trigger pin is trying to see if it's lower than about 1/3 of the power supply voltage. Once it goes above about 1/3 of the power supply voltage, the pin does nothing, and that's when we are at our stable state. It's unstable while we have a low signal to the trigger pin, plus about 1.1 seconds. There we go. It sets the output high, even if the trigger input drops below 1/3 of the power supply voltage for just a fraction of a second. So, in any case, light dependent resistor, very simple component. Its resistance changes based on how much light is falling upon it. And we have it wired as a voltage divider here. And depending on the resistance here, we will get a voltage of the power supply voltage, a fraction of the power supply voltage, depending on how much light is falling on it. So that you can see with this amount of light we have about 2.7 kilo ohms of resistance. Make sure you look up here for the kilo ohms, and when I put my hand on it you can see that the resistance goes up, and 26.5, there's 13 kilo ohms. So if we get it a lot darker, it should get to about an infinite amount of resistance. So let's measure the resistance again. Lost my connection there. So that's about 6 kilo ohms right there. Put my finger over it, and we have about 80 kilo ohms. So it's not hard to make it pretty dark on there and raise the resistance significantly if you get enough light on it. Let's try to get it pretty bright. We should be fairly close to 0 ohms of resistance. So I haven't measured it out in the sun yet, but there you go. You can see it's about 450. So 400, if I get the lamp closer, you can see how rapidly it's going down like that. So I think in sunlight you'll get to practically 0 ohms of resistance. So in any case, hopefully that all made sense. The main takeaway is when you're learning these circuits and you're learning new components, try to figure out a really simple way to integrate that new component you'll learn with circuits you already know, because generally you get a demonstration circuit, but it's expected that you're going to take what you learned from that circuit, which is limited, and start stacking on other topics that you learn to that circuit to make it do more interesting things. So thanks for watching. Make sure you turn the meter off when you're done, and I will see you in the next video.